Good afternoon. So the title of my presentation is Gaussian process modeling of solutions to partial differential equation models with information from boundary and initial conditions. So I work in the area of design or experiments, and in our community we are interested to construct emulators or surrogates for time-consuming simulators. So in this talk, I will talk about the problem of building Gaussian process or GP emulators for time-consuming finite element simulators that use information from Differential boundary and initial conditions. So as most of you know, the finite element method is a numerical method for solving partial differential equations with some additional initial and boundary conditions imposed. Okay. Okay. So just to illustrate, I use a simple example. So initial boundary value problems are commonly used to model physical phenomena. So like the temperature in this plate. Okay. So this plate has thickness h. So it experiences convective heat transfer with the surrounding air. So standard model for this problem is the heat equation. So these are some parameters. So to solve this partial differential equation for unique solution, we need to impose boundary and initial conditions. Okay. So popular boundary conditions like Neumann boundary condition, Robin boundary condition, and Differential boundary conditions. So we are particularly interested in Differential boundary and initial conditions in this talk. Okay. So at the bottom h, okay, the temperature is set equals to G1, a function G1. So it's because h is S2 equals to 0. So G1 is a function of the space. So the spatial coordinate S1 time t, and this Differential boundary condition G1 is parameterized by this parameter x1. Okay. And at the top boundary, the Differential boundary condition, okay, which means we set the temperature equals to some function G2, okay, is parameterized by parameter x2, and at time 0 we need to impose an initial condition. So the temperature, this initial condition is the temperature is equal to G0, some function G0, and it's a function of spatial coordinate S1, S2, and is parameterized by parameter x3. So this parameter, when we change them, we change the Differential boundary and initial conditions. Okay. So notice that actually the original 3D model is simplified into a 2D model. That means the temperature depends only on two spatial coordinates S1 and S2. Because the thickness of this plate h is small. Okay. And so the initial boundary value problem for this plate temperature can be written in this form. So the first equation is the partial differential equation. So you want to solve it for the temperature capital T at spatial coordinate S and time t. Okay. And this S is the spatial domain. The time interval of interest is 0 zeta. So here the Differential boundary conditions are written down formally as follows. The temperature is equal to function G1 at Differential boundary ds1, and temperature equals to function G2 at Differential boundary ds2. So the initial condition is the function G0. Okay. Notice that G1, G2, and G0, they are parameterized by the vector x. Okay. So we change the parameters, we change the Differential boundary and initial conditions, which will change the PDE solution. So why this? We introduce this parameter because of our interest in uncertainty quantification. So there are often uncertainties in what's the appropriate Differential boundary condition or initial condition to use. So the parameters here are the uncertain parameters, okay, in uncertainty quantification. This initial boundary value problems can be difficult to solve analytically. So in practice, numerical methods are often used. One popular method is the finite element method, which I will briefly discuss. So in this finite element method, the spatial domain is partitioned into triangles. So we do a triangulation of the spatial domain, okay? And as you know, within each triangle, the PDE is approximated with a polynomial. So the PDE solution is approximated with a piecewise polynomial function over the whole domain. Okay, then this piecewise polynomial function is constrained to be continuous. So associated with the triangulation are a set of points called the nodes. So these nodes are used to generate the functional basis for the piecewise polynomial approximation. For this continuous piecewise linear polynomial approximation shown in this figure to the right, okay, the nodes are the vertexes of the triangles, also called elements, okay. So for a fixed time point, the the functional bases are also called 10 basis function, okay, and there is one 10 basis function for each node. So this 10 basis function phi I is 1 at node Si, okay, and is 0 at the other nodes. So for fixed time point, the temperature or the PDE solution is approximated as a linear combination of this 10 basis function. So the coefficient is beta it. Due to this property of the 10 basis function, the temperature at node Si and time t is actually the coefficient beta it, okay. And we can also do this for the time domain. So we use a set of nodes in the time domain to generate the 10 basis function. So finally, our PDE solution is approximated as a linear combination of the product 10 bases, okay, phi I s and phi j t. The coefficients are the temperature at spatial node Si and time node Tj. So these coefficients are obtained by solving algebraic equations, okay. So in practice, we would tend to use fine triangulation and many nodes to solve the partial differential equation. And so shown like this kind of finite element mesh, okay. And shown here is a solution of the plate temperature problem at time 12,000, okay. Now, an important problem in uncertainty quantification is to quantify the effect of uncertainty in Differential boundary and initial conditions on the PDE solution. So a straightforward way to do this is just by Monte Carlo simulation, okay. We generate random Differential boundary and initial conditions, then we solve the PDE. So we get a random sample of PDE solutions, okay. But solving PDEs can be time consuming, so it can be more computationally efficient to construct emulators or surrogate to replace the finite element simulator. So to construct this emulator, we do a so-called computer experiments, okay. That means we change the input vector to the simulator x, okay, which would also change the Differential boundary initial conditions and other parameters. So we change them according to experimental design, and then we collect the data, which are the PDE solutions obtained by running the finite element simulator at the chosen values of the inputs x, okay. So we denote from now on we denote the PDE solution as at input vector x as fx dot, okay. And we assume there is a Differential boundary condition G1, okay. It's a function of spatial coordinate s time t parameterized by x, and it applies to the Differential boundary ds1. and there's an initial condition G0, okay, function of spatial coordinate S and parameterized by X, okay. So this G1 and G0, we assume they are cheap to compute, or they are known, okay. So we can readily use them to improve the construction of the surrogate or emulator. So this G1, G0, they are not some output from some other time-consuming simulator, okay. So to summarize, we know that the PDE solution, okay, F, satisfies these two equations. So F is equals to the differential boundary condition G1 at the boundary differential boundary ds1, and F is equals to the initial condition G0, okay, at time 0. So existing surrogates for computer experiments for often treat this simulator as a black box, okay. We just get data, we construct the emulator surrogate. So we ignore this information that we have, okay, for that we can use to improve the construction of the surrogate. So our main contribution is to propose a GP model, okay. The GP model is indexed by the simulator input X, spatial coordinate S, and time t. And this GP model is constrained to give predictions that are exactly equals to the differential boundary and initial conditions at, that are imposed on the simulator. So in particular, this Y is equals to the differential boundary condition G1 at boundary ds1, and Y is equals to initial condition G0 at time 0. Okay, so this intuitively this would help improve the prediction accuracy of the surrogate. Okay. Also, our proposed GP model is designed to be tractable when the PDE solution is observed on a large node set. Okay, so this is important because a main factor that causes the finite element simulator to be time consuming is the use of a large node set to solve a PDE. So changing differential boundary conditions can cause significant changes to a PDE solution. Okay, like here we let the temperature. This is a plate temperature problem. Okay, so the temperature at this lower edge S2 is 0, temperature upper edge S2 equals 1. They are linear functions with some intercept and slope that are parameters. So if we change them, we can cause significant changes near the boundaries, okay, cause significant changes to a PDE solution near the boundaries. So this is probably more interesting from a practical point of view. So this example is about cancer treatment via hypothermia. So this process attempts to kill the tumor by raising the temperature in the tissue high enough with an electric field. Okay. So this center part is the tumor, and directly above the tumor on the skin surface there is an electrode, and directly below the tumor on the skin surface we place another electrode. So the potential difference will create some electric field which will hit the tissue between the two electrodes. Okay. So some authors consider a much simplified model for the problem like shown here. Okay, and so tumor is approximated as square. And so the temperature at this top edge and bottom edge are given by the differential boundary conditions. Okay, so actually they are the temperature of the skin surfaces which are controlled through the use of cooling pad. So it might be of interest to study the effect of changing the temperature at the skin surface because we can change it by changing cooling rate of the cooling pad. Okay, we study the effect of changing this differential boundary condition on the temperature in the tumor and the healthy tissue. So I will revisit this example later. So there are some other examples you can find in the literature where the authors are interested to quantify uncertainty in differential boundary and initial conditions, like groundwater flow model, spiral transistor model, and the Burgers equation. So I will now mention some existing Gaussian process emulators that can be used to predict functional outputs like PDE solutions. So some notations. So x is the vector of inputs to the simulator, and fx dot is the PDE solution, which is observed on the set M. Okay, this set is a set of nodes which I just denoted by S1 to S capital N. Okay, the experiment design is D, and it consists of points x1 to x lowercase n. So this means that we set the simulator input x to x1. We run the simulator to get the PDE solution, and then set it to x equals to x2, run it to get the PDE solution. So we use all these n lowercase n PDE solutions to construct our emulator. And the standard model for functional outputs like PDE solution is based on assumption of covariance, stationary, and separability. Okay, so we assume a covariance function that is separable with respect to the S, which is the space-time coordinate, or just spatial coordinate. Okay, and X is the simulator input, so it's the product function. Okay, so because of this, you can get the experiment data is some normal distribution with this covariance matrix. Okay, sigma z squared is the variance multiplied by the Kronecker product of two correlation matrices. So R1 is the correlation matrix for the these nodes. Okay, that gives the correlation between node points, and R2 is a correlation matrix that gives a correlation between experiment design points. So we can use computationally efficient formulas to fit this GP model based on the use of Kronecker product matrix algebra formulas. But because in finite element simulation, the number of nodes capital N here can be very large, the inversion of this R1 correlation matrix, which is capital N by capital N in size, can be very time consuming. Okay, especially if you use some correlation function that doesn't taper off to zero, so the matrix will be full matrix, so very difficult to use this GP model. So a more computationally efficient alternative is what I call the KRG GP model. KR stands for Gaussian law F. So this GP model only predicts that the PDE solution at the spatial nodes y1 to yn. So it consists of a collection of vectors y, x, okay, with components yx, s1 to yx, sn. So this is should be the correct way to proceed, okay, because the simulator output is actually a linear combination of these 10 basis phi I with coefficient f x si. So si are the nodes, okay. So this is the form that the approximation and the finite element method use. So our simulator output should match with our emulator should match with the simulator output, okay, which should be of this form. So these coefficients yx, si, they are predicted with the KR GP model. So the KR GP model assumes the covariance matrix of yx and the mean vector of yx. They are these constant, okay, they do not depend on x. And this sigma here, we denote this eigen decomposition by phi lambda phi transpose, okay, phi n by n matrix of eigenvectors and lambda diagonal matrix of eigenvalues. So we can rewrite the model, GP model, in this form, okay. Yx is mu plus phi times lambda raised to the power of half psi x, okay. This psi x consists of IID standard normal random variables for fixed x, okay, so psi 1 x, psi n x, and we assume the collection of psi I as x varies is a GP, okay, Gaussian process with a correlation function Ri with parameters theta I. So because of this assumption, this is the covariance between yx and yx prime, which is in general not separable, okay. So this is not the separable GP model. We mainly use a very simple method so that the KRGP model is very computationally efficient. We use a simple method to estimate these parameters. So this mu here is estimated by the sample mean of the PDE solutions. The covariance matrix sigma is estimated by the sample covariance matrix of the PDE solutions that we get in the experiment. And so we can use the estimates to estimate the random process values at psi I at the experiment design point x1 to xn. So we do not estimate at psi I hat x1 to psi I hat xn. So we update the prior process of psi I. So these are the prior process of psi I with this estimated data, and then we plug in the updated process back into this form to get our predictive process. Okay, so I won't talk much about details. So it's just want to mention that it is much computationally efficient because we only need to compute eigen decomposition of the sample covariance matrix once. Okay, and most of its eigenvalues of this sample covariance matrix is 0. Okay, but standard separable GP model require inversion of this capital N by N matrix many times in the fitting of the model. So now the KRG GP model does not automatically satisfy the Dirichlet boundary and initial conditions. So here is what we propose to do to force it to satisfy the conditions. So the Dirichlet boundary and initial conditions they are applied on a subset of the space-time boundary. Okay, so we let the nodes at that part of the space-time boundary be denoted by the set B. Okay, and it consists of points U1 to U tau. So these are the nodes at that part of the space-time boundary. Then we can write this Dirichlet boundary and initial conditions compactly as in this form. F x s t is so the PDE solution at simulator input x, spatial coordinate s, and time t is equal to some function lowercase q. Okay, for all x in the experiment region chi and st in this finite set B. So q here is the function that assigns a value to a Dirichlet boundary node according to the Dirichlet boundary condition, and q assigns a value to a node at time 0 according to the initial condition. Okay, because this experiment region chi is an uncountable set, so it's often a convex and compact set. Okay, like a hypercube. So we can update the standard GP model with this equation. Okay. So what we propose to do is to interpolate the Dirichlet boundary and initial condition first with an inverse distance interpolator, capital Q here. So this capital Q interpolates Qx U1 to Qx U tau. The values at the Dirichlet boundary nodes and the nodes at time 0. Okay, with this inverse distance interpolator, which means that the weight for Qx Ui is the inverse of the square distance dh squared between the space-time point SD at which we want to predict and the node Ui. Okay, so these weights are normalized. So you see we divide by the sum of the weight. Okay, so Q is a convex combination of the values at the Dirichlet boundary nodes and the nodes at time 0. Okay, so this dh we take is a distance metric with parameter h. Okay, so dh square is a Euclidean distance. Dh square between the distance square between st and s prime t prime is the Euclidean distance between the point s and s prime plus a parameter h times the square difference between the times t and t prime. Okay, so we need to introduce parameter h here because space and time they are measured in different units. Okay, so we select h by minimizing the sum of square difference between the experiment data and the inverse distance interpolator, capital Q here. After we having constructed the inverse distance interpolator, we take the difference between the experiment data and the inverse distance interpolator, which is f minus q. So we model this residual with the KRG GP model. Okay, and so our final model is the KRG GP model for the residual, which is denoted here y plus the inverse distance interpolator q. So it can be shown that this model, okay, called modified the KRG GP model, it satisfies the Dirichlet boundary and initial conditions almost surely. In contrast, the standard separable GP model and the KRG GP models do not, it's not guaranteed to satisfy Dirichlet boundary and initial conditions. Okay. So some numerical examples. So I revisit the problem of cancer treatment via hypothermia. So the tissues which contain the tumor is heated with an electric field. Okay, in this treatment. So the objectives are to find conditions under which the temperature is in the tumor exceeds 42 Celsius and the temperature in the healthy tissue does not exceed 42 Celsius. So this will kill the tumor. So two PDEs are used to model as models. Okay. So the first is the Pence equations, which gives the temperature in the tissue, and the second one is the potential equation, which models the electric potential in the tissue. So these are coupled. So we consider only the steady state time independent case. One of the parameter of this simulator is the frequency of electromagnetic wave. Okay, so it affects the conductivity and dielectric permittivity of the healthy and tissue and tumor through these COCO models. And so this is our spatial domain. So we only consider a simplified problem to demonstrate so that we can do many simulations to compare the different emulators. Okay, so this is the spatial domain and the finite element mesh. So the tumor is raised squared. Another simulator input is X2, potential difference between the electrodes, and this X3 and X4, they are Dirichlet boundary conditions. Okay, X3 gives the temperature at the top edge and X4 gives the temperature at the bottom edge or bottom boundary. So we call that these are the temperature of the skin surfaces, which we may control by changing the cooling rates of the cooling pad. So the other variables, input variables X5, X6, X7, X8, there are some other parameters in the PDE, and these are the ranges of the variables for our computer experiment. Okay, so this figure illustrates the inverse distance interpolator QXS. So this Q here only depends on X3 and X4. Okay, because the Dirichlet boundary conditions only depend on these two X3 and X4 and not the other Xi's. Okay, here I plot the inverse distance interpolator when the X3 is 36, so the temperature at the top edge is 36, and X4, the temperature at the bottom edge is 28. So it can be seen that this interpolator is approximately a linear function that connects the temperature at the top edge to the temperature at the bottom edge. So I perform a replicated simulation. So I generate 30 Maximin Latin hypercube designs of size 56 and another 30 of size 8, another 30 Maximin Latin hypercube designs of size 80. Then I get the data from the finite element simulator and I feed the three models. Modified KRG GP model, which is the proposed model that incorporates the Dirichlet boundary condition, the separable GP model, standard separable GP model, and the KRG GP model. Okay, shown in the top figure are the box plots of the mean absolute prediction error for the three models. So we see that for the same sample design size, okay, the modified KRG GP model tends to give a smallest mean absolute prediction error. So we compare these three box plots, okay, and for design size of 56, and these three box plots for design size of 80. So similar results are obtained for the mean absolute prediction error as shown in these box plots. So the coverage of the modified prediction intervals of the modified KRG GP model tend to be closest to nominal. Okay, so these box plots show the coverage of nominal 98% prediction interval. So the nominal coverage is 0.98. Okay, shown by this dashed line. So these are box plots of the modified KRG GP model. But these standard separable GP model tend to suffer significantly from under coverage. Now, for fixed design size, the modified KRG GP model tend to give prediction intervals longer than the separable GP model, but shorter than this KRG GP model. But these shorter prediction intervals of separable GP model come at the cost of poor coverage. Okay, so this is not good. So as shown by this last box plot, the modified KRG GP model and KRG GP model take only a few seconds to fit. Okay, but the standard separable GP model can take 2,000 seconds to fit for design size of 56 and more than 2,500 seconds to fit for design size of 80. So overall, the modified KRG GP model gives the best prediction performance and is computationally efficient. So this is the end of my talk. Thank you for listening.
No question, just skip again.
Okay.